Welcome to this new class. In the last class, we discussed about the dimension theorem, and we proved that if U and W are the two subspaces of a vector space, we have to prove this result. U and W are two subspaces of a vector space V. Then we can say that the dimension of U plus W is the same as a dimension of a U plus dimension of a W minus dimension of a U intersection W. And also we check if we have a if W intersection U or U intersection W is equal to the 0 subspace, then we can say that simply is equal to dimension of U plus W is equal to dimension of a U plus dimension of a W. And then we prove some discuss some examples. In the last example, we discuss about the calculate the dimension of a U plus W, calculate the dimension of a U intersection W, verify this theorem, and we also use the method for extending the basis. If we have and also when we calculate the basis for a U plus W is more than n element, then dependent we have to exclude the some elements, choose element which has belong to the span of the its preceding elements, and then okay. So now today's class we discuss about the coordinate vector and coordinate matrix of a vector space. So coordinate vector means we have a any set of a vectors. We have suppose we have a set of vectors equal to v1, v2 up to vn, and any vector we can root elementary vectors we choose as a vector space V. We have a V is a vector space, and then we can say that over a field of real or whatever the field we have to. If this is the element of a vector space V, and we have to choosing this is a suppose this is a basis of a this element of a basis of a vector space V, and we choose any element V, arbitrary element for the belongs to V. Then by the definition we can say that V can be written as a finite linear combination of the elements of a basis. Why? Because basis is a span of a basis means you have a if it is basis, this is a two things is equal to it is a linear independent, and also we have a span of B is equal to we have a V. So by this property span of V arbitrary chose element of a V, then this every element of a this V can be written as finite linear combination of the elements of a this. So we have a alpha to V2 and so on. We have a alpha and Vn, where we have a this alpha 1, alpha 2 up to alpha n are scalars. So these alpha 1, alpha 2, alpha n are scalars. So this means we can say that these scalars is called is the this alpha 1, alpha 2 up to alpha n is called is a coordinate vector. Coordinate vector, and we have to denote it as a this V, which corresponding to this basis is nothing but is equal to have alpha 1, alpha 2 and alpha n. Now, if coordinate matrix is simply this, we have to write the this is we just say that elements of this this coordinate vectors as a column of the matrix. So if we write the in the form of a matrix of this, B can be written in the form of a alpha 1, alpha 2 up to alpha n, and then this for corresponding to matrix this. If we have to choose another vectors, then we have a particular vector V can be written as a uniquely. This V can be written as a uniquely linear combination of this. If we take a U also belongs to V, so then this U also can be written as a uniquely linear combination of these vectors beta 1 V1 plus beta 2 V2 plus so on. You have a beta and Vn, and then this U is corresponding to the basis B is vector is equal to beta 1, beta 2 up to beta n, and then the matrix of this we can say that we have a beta 1 up to beta n, and then complete matrix of this is a beta corresponding to the first element, corresponding to the second element, and so on. We put into the columns, then we can calculate into a this form. So now we can just say property definition. We have a b is equal to v1 v2 vn be an ordered basis. This is a very important things. We have a ordered basis. This is the order of the basis is important here, because we have to writing the when writing the coordinate vector or coordinate basis for a matrix for a vector space v, and v an arbitrary, then v can be written as a, this is a unique representation, you just know that. So if v is a unique representation, then we can say that the elements of this, the scalars alpha and alpha 2 are the coordinate vector of a v relative to the ordered basis b, and this is equal to this. Because why this is order? Order is important. This is order when you calculating this order should be, or the basis element should be the very important. Otherwise we have to, if we have to write change the order of this, then this should be alpha 2 and alpha 1. So this accordingly this coordinate vector is also change, we have to write. So now if we just arrange a column b, this means we have to this b is a suffix, we have to why we have to, this means we notice this is a u or b. As b below indicate that alpha 1 alpha 2 are the coordinates of b relative to b. Here is u, this is not u, this is v, sorry. So this is v. So this means this way we can say that simply we can say that we have to notation is denoted by this. So b is suffix. So b below indicate that the alpha 1 alpha 2 are the coordinate of a v relative to this basis, because we have a number of a basis, but we have a different number of a bases are there. So corresponding to every basis we have a u calculate is a different scalars, and that means this means we have to say the coordinate vector of a u corresponding to that basis is there. So this means u sub b suffixes means mention is a whatever basis we have to choosing, ordered basis is choosing corresponding to that ordered basis. These are the coordinate vectors of a this thing. Okay, now just as a coordinate matrix or coordinate vector, you can say that v is related to the b is the column matrix of Rn, whose components are the coordinates. Means is a column matrix of the this, so we can calculate into this form. This is again, this is v, not a u, sorry. So u is equal to L, we can choosing is a v, so this should be v corresponding to the b. So you have alpha 1 alpha 2 alpha n, and then we have to if we have another vector, so we have to calculate the another column and so on. So this means coordinate matrix, or we can say that v related to basis is a column matrix of in Rn we have to represent in whose components are the, and these components are the nothing but is equal to is the coordinates of a v. This vector space is the. Now since this is very important, we have to just write v, this is b, okay. V can be written as alpha 1 v1 alpha 2 vn up to n, and v is related to the basis b is a unique. Suppose we can write v is another representation is there, beta 1 v1 plus beta 2 v2 and so on. We have a beta and vn because of v1 v2 vn is a basis. So we have a, clearly we have a v1 v2 vn is a basis. So this is a basis for a vector space v. So this expression is a unique, means we can represent another this. So this means by these two we can say that similarly this is can be written as a alpha 1 v1 and so on, alpha and vn is equal to same is equal to beta 1 v1 plus so on, so is equal to beta and vn, and this can be written alpha 1 minus beta 1, we have a v1 plus alpha 2 minus beta 2 v2 and so on is equal to alpha n minus beta n, and vn is equal to 0 vector. And because this v1 v2 vn are is a basis and this is a linearly independent, so this implies that alpha 1 minus we have alpha 1 minus beta 1 is equal to 0, alpha 2 minus beta 2 is equal to 0, and so on. And generally you can say that we have a alpha n minus beta n is equal to 0, means alpha 1 is equal to you have a beta 1, and so on. You can say that alpha n is equal to you have a beta is equal to this. So this means the means unique. So this means V. This is V. So corresponding V we have alpha 1. Corresponding V have a taking is these two coordinate vectors. So this means if this is this, the coordinate vectors are same only equal if we have these two equal, means alpha 1 is equal to beta 1 and alpha 2 is equal to beta 2 and alpha n is equal to beta n is there. So this way we can say that this representation is unique. Now coordinate system may be convenient tools for calculation. If u and b are there, then we have to calculate the sum. We can just take a alpha of u corresponding to the b. We can just, this is nothing but is equal to alpha alpha 1, alpha alpha 2, and so on. We have a alpha alpha n, and if we calculate the coordinate vector of this alpha of v corresponding to the basis is same basis b. So we can just write in the form of this. We take some different scalar here. So we take some beta. So we have a beta beta 1, beta beta 2, and then we have a, we can just say that, and so on, beta beta, and this, if we calculate the coordinate vector alpha u plus beta v corresponding to the this b, and now this is nothing but equal to, we just say that we write as a column vectors of this plus this is equal to this. So this means this is can be written in the form of this alpha alpha 1, alpha alpha 2, and so on. As a similar fashion we just write into this form. I just said. Okay, so this means can be represent is a linearity condition. So we can say the said scalar multiplication of these and scale. So this is also represent into a this form. Okay, first let's begin with example. Suppose we have a vector is giving in this in R3 relative to the standard basis. If relative to standard basis means we can say that -2, 1 and 3 is clearly written in the form of -2, 1, 0, 0 and plus 1 into times 0, 1, 0 plus 3 times of a 0, 0, 1. So clearly we can say that -2, 1, 3, this is a vector and this is coordinate vector corresponding to this basis is equal to, you have a -2, 1 and 3, or if we take a is a matrix form, so just write in the form of this, you have a -2, 1 and 3, or you can just take a transpose of a this thing in the matrix. So the coordinate vector of a any vector with relative to the standard basis is the itself. So we just say that because if we have a basis or standard basis are there, so that means we can say that the coordinate vector can be collected as it is, because this is the same can be written as a linear combination of these vectors. So this means if we have a this is standard basis, then this the same if we have it. So this means we can is equal to it in this form. So coordinate matrix V related to the standard form is equal to, we have to just say that in this form the components of V are the same as a coordinate relative to the standard basis. So the component of V are the same as a coordinate related to the standard basis. If we have a standard basis, then whatever vectors we have to written in the linear combination, they come coordinate vector are the same of these scalars into this form. Okay, so now we have some different example. This is again we have to take a standard basis of a V4 is not mentioned by just writing the standard basis. So means we have a this vector is standard basis means we have a E1 and E1 is the uniform 1, 0, 0, 0 because of a V4, and you have a E2 can be written as a 0, 1, 0, 0, and now you have a E3 is a form of a 0, 0, 1, 0, and you have a E4 0, 0, 1, sorry 0, 0, 0, 1, and that means we can say that this vector 2, 3, 4, -1 can be written in the form of a 2 times of a E1 plus 3 times of a E2 plus 4 times of E3 plus or minus 1 times of E4. That means we can say that the coordinate vector of a 2, 3, minus 4 is corresponding to the standard basis. This is a B. You can say that basis is nothing but is equal to, we can say that 2, 3, 4, minus 1, and the matrix of this is equal to 2, 3, 4, minus 4. In the matrix notation we are writing this one. So now let us try some different types of um, basis. We have to take a standard basis is much easier. That means if we have a giving the standard basis, so the coordinate vectors of this is a vector itself, and the matrix is this matrix. You take a transpose of this as the columns of a this matrix representation. Now I take this same vector previous one, but I change the basis. I take a basis is not a standard basis. So this means we can just say that we can write 2, 3, 4, minus 1 in the form of alpha 1, 1, 1, 0, 0, plus you have a I just take alpha 1, sorry, alpha 1. Now we have a alpha 2, 0, 1, 1, 0, plus alpha 3, 0, 0, 1, 1, plus alpha 4, 1, 0, 0, 0. Now this can be written in the form of this. You have a, this is alpha 1 and no other, this you have alpha 1 plus alpha 4. Now you have a alpha 1 plus alpha 2, no, all other are 0. Now we have a alpha 2 plus alpha 3, and then we have a just that alpha 2 plus alpha 3, and now this is 0, this is 0, this is 1. So you have to just say that alpha 3, rest of them 0. So we have to just write this in the, these are the equal. So we have a alpha 1 plus alpha 4 is equal to 2. Now we have alpha 1 plus alpha 2 is equal to, you have a 3. Now we have a alpha 2 plus alpha 3 is equal to 4, and then we have a alpha 3 is equal to minus 1. So alpha 3 is equal to minus 1, this implies that, and that means alpha 2 is equal to 4 plus 1 is equal to 5. If alpha 2 is equal to 5, then by this equation we can say that alpha 1 is equal to 3 minus 5 is equal to minus 2, and then alpha 1 is equal to minus 2. So we just by this equation we can say that alpha 4 can be written in the form of a 2 plus 2. So 2 plus 2 is equal to 4. So we have to get this 2, 3, 4, minus 1, and this is corresponding to the related to the basis B. The coordinates are alpha 1 is equal to minus 2, and then you have a alpha 2 alpha 2 is equal to, we have to calculate alpha 3, sorry, this is alpha alpha 2 is equal to, you have a 5, and alpha 3 is equal to, you have a minus 1, alpha 4 is equal to, you have a 4. Now this is not the same, but in the previous case we have to for corresponding the standard basis, this vector remain the giving the same values, but here this is giving you a different value. In the matrix notation we can just say that minus 2, 5, minus 1, and 4, and this is the corresponding to the vectors this thing. So minus 2, 5, and minus 1 and 4, this is a vector we have to calculating into a coordinate vector of this. Let's some example, more example, some more different types of a coordinate vector matrix we have to calculating corresponding to the this basis vector V, and the basis is giving this. So this is clearly again 1, 2, minus 1 can be written as alpha times of a V1. Alpha times of a V1 means V1 is equal to, you have a 1, 0, 1, plus beta times you have a 0, minus 1, 2, plus gamma times of a 2, 3, and minus 5, and this can be written as a, you have a this alpha plus 2 gamma. Alpha is equal to 0 minus beta plus 3 gamma, and now you have a alpha plus twice beta minus 5 gamma. So this can be written as a alpha plus 2 gamma is equal to 1, and you have a minus beta plus 3 gamma is equal to, you have a 2, and you have a again alpha plus twice beta minus 5 gamma is equal to minus 1. So by this we can just say that from this equations we can say that alpha can be written as a 1 minus 2 gamma, and from here you can say that you can just as a beta can be written as a, we can bring is this, you have a 3 gamma minus 2. So if you put the alpha and beta here, so alpha is equal to minus 2 gamma plus 2 beta, 2 times of a 3 gamma minus 2 minus ka 5 gamma is equal to, you have a 1. So you have a 1, you have a just 1 minus 2 gamma plus 6 gamma, and then you have minus ka 4, and then you have a minus ka 5 gamma is equal to 1. 6 gamma, 5 gamma, you have a, and so you have a clearly is equal to minus gamma, and minus 3, and the minus gamma is equal to 1 plus 3, and then this implies that gamma is equal to minus ka 4, and if gamma is equal to minus 4, then 1 minus plus 8 is equal to, you have a 9, and then you have a beta is equal to, you can say that you have a 3 gamma, so you have a minus ka 12, minus 2 is equal to minus ka 14 in this 4. So this means we can say that corresponding this vectors corresponding of this, so we have a v corresponding this basis is equal to alpha is equal to, you have a 9, and then you have a beta is equal to minus 14, and gamma is equal to minus ka 4 is there. So this way we can just say that we can simplify this. So this equating the coefficient into this form, and then you can just say that this is equal to this form. We can just say that 5 alpha 1 is equal to 5, alpha 2 is equal to minus 8, alpha 3 is equal to, you have a minus 2. So we can be written in the form of a 5 minus 8 and 2. This we can be represented into this form. So in the previous we have some mistake here, some calculations. So but this is the correct calculation is there. We have to solve the system into this form. So this is we have a, I think so I have to make a mistake somewhere here. Okay, yeah, this is correct. So this correct is this, we can say that this is equal to, you have a 5 minus 8 and 2. So one more problem we can try for calculate the coordinate vector for the polynomials. This is equal to polynomials. So this can be written in the form of, we can say that 3 minus x minus 2x square alpha times 1 plus x plus beta times 1 plus x square plus gamma times x plus x square. This can be written as a constant term. We have alpha plus beta term, beta we have a coefficient of x, you have a alpha plus gamma x, coefficient of a x square, beta plus gamma x square. So this implies that you have a alpha plus beta is equal to 3, now alpha plus gamma is equal to minus 1, and then you have a beta plus gamma is equal to minus 2. So if we have to just subtracting these two, first and third, so you getting the alpha minus gamma is equal to, if you subtracting this is equal to 5, and then you have a alpha plus gamma is equal to minus 1. If you adding these two, to 2 alpha is equal to 4, so alpha is equal to, you have a 2. If alpha is equal to 2, then beta is equal to, you have a 1, and if alpha is equal to 2, you have a gamma is equal to, you have a minus 3. So you have a 2 minus 1 and minus ka sorry 2 1 and minus 3 are the coordinate vector of this corresponding to the this basis is there. So 2 1 and 3 are the corresponding to this. This is clearly we can just say that. So we just calculating in this form. So we have to take into a this form. So this is clearly we can say that we have a write into a this form, gamma is equal to, you have a this form. So 2 1 and 3 are the this is where we have to make a mistake. I just take alpha minus beta is equal to 3 plus 2 is equal to 5, and you have alpha plus gamma is equal to minus 1. When we adding these two, this is 4, alpha is equal to 2 is no problem. If alpha is equal to 2, then beta is equal to 1 is also is no problem. So beta is equal to 1 is no problem. And now if we have a beta is equal to 1, if beta is equal to, you have a 1, and alpha is equal to, you have a 2. So gamma is equal to minus 1 minus 2 is equal to minus 3. This 2 is minus 3 should be there. So this is mistake is here. Here is a minus 1. So this means VB is equal to, this is not correct. So this is correct one is equal to, you have a 2 1 and minus 3. This is a vector, and if we, this is in the form of a matrix, 2 1 minus 3 is this thing. Okay, so now one example related to the matrix. Previously we have to example was related to the binary of this is polynomials. Now this when also we have a vector is giving into this over 2 by 2 matrices over the real field, and a1 a2 this is, sorry, this is a1, and this is can be written in the form of a2. This is you have a a3, and this is you have a a4. So we can write the element of a, this means 3 minus 2 0 1 can be written in the form of a alpha times of a a1 plus alpha 1 alpha 2 times of a a2 plus alpha 3 times of a3 plus alpha 4 a4 a4. And now we have to just check this is can be written in the form of, in this form with this alpha 1 minus alpha 1 0 0, and then we have a second is this, you have a 0, you have a beta 0, and then we have a sorry, this is not beta, this is alpha 2, sorry, alpha 2, and now we have a alpha 3 0 0 0. Now we have a last one is alpha 4, so 0 alpha 4 0 alpha 4. Now this can be representing this 0 alpha 3 and 0, so alpha 1 plus you have a alpha 3 minus का alpha 1 plus का alpha 2, and then plus का you have alpha 4. This is 0, this is alpha 2, rest of them is equal to 0 0 0 0, you have alpha 4. So by this we can say that alpha 4 is equal to 1, alpha 2 is equal to, you have a 0, and then you have a alpha 1 minus alpha 1 plus alpha 2 plus alpha 4 is equal to minus 2. Alpha 2 is equal to 0, is equal to 1. So alpha 4 is equal to minus 2, and this is equal to plus 1 is equal to minus 1. And then we have alpha 4 is equal to minus 1, and alpha 1 plus alpha 3. So alpha 1 plus I'm sorry, this is alpha, sorry, this is wrong. No, this is alpha 2 is equal to 0 is okay. And then we have to calculate this alpha 4 alpha 2, so minus ka alpha 1 plus ka alpha 2 plus alpha 4 is equal to, you have a minus 2, alpha 2 is equal to 0, alpha 4 is equal to 1, so minus alpha 1 is equal to minus 2 minus 1 is equal to minus 3. So alpha 1 is equal to, you have a we can say that alpha 1 is equal to, you have a 3, and if alpha 1 is equal to 3, then we can say that we calculate the form of alpha 3. So alpha 1 plus alpha 3 is equal to 3, then alpha 3 is again is 0. So this means this this corresponding to the this we have a getting the matrix coordinate vectors of this corresponding matrix is equal to, you have alpha 1 is equal to, you have a 3, alpha 2 is equal to, you have a 0, alpha 3 is equal to 0, alpha 4 is equal to 1, and if you write a coordinate matrix, this is equal to 3 0 0 1 in this form. Okay, so this is 3 0 0 1, we have to calculating into this form. Okay, so now this is the same questions, but just interested in the last part, rest of them for your home assignment. So we try to discuss only this fourth part here, and then rest of them is home assignment. This means we have a basis into this form. So that means we can write coordinate vector of a. So v is equal to, we have a given minus root 2 pi e, and this can be written in the form of a, this can be written as a alpha times of a 2 1 0 plus beta times of a 2 1 1 plus gamma times of a 2 2 1. and this implies that we can write directly 2 alpha plus twice beta plus 2 gamma is equal to minus root 2, and then we have this is a pi, sorry, this is you have a pi. So this can be written as alpha plus beta plus 2 gamma is equal to we have a pi, and then we have a beta plus gamma is equal to you have a e. Now if we multiply the third equations by 2, so we can just multiply it by 2, so we getting the 2 beta plus 2 gamma is equal to twice e. And now by this first equation we can say that, so 2 alpha plus 2 beta plus 2 gamma is equal to you have a twice e. Twice e is equal to minus ka root 2. So twice alpha is equal to minus root 2 minus ka e. Sorry, twice e. So alpha is equal to 1 up minus ka 1 upon root 2 minus ka e. So we have alpha is equal to this form. And now if alpha is equal to we have this, so we calculate, substitute the value for alpha here. So we just from these two equations we get in this in the form of this beta plus 2 gamma is equal to pi minus alpha. So minus alpha is equal to you have a we have a plus, so we have a plus 1 by 2 root 2 plus ka e, and then you have a also is equal to beta plus gamma is equal to e, and then you have to just subtract these two, so this is cancel out. So gamma is equal to you have a pi plus 1 by 2 root 2, and this is cancel out. So gamma is equal to you have a this, alpha is equal to this, so we have to, if we gamma is equal to this, then we have to beta, so beta is equal to you have a e minus gamma is equal to minus pi minus ka 1 upon 2 root 2. So this means we can say that this is the coordinate vectors of this. Clearly we can say that the coordinate vector of this in the form of alpha is equal to you have a minus 1 by 2 root 2 minus e, and then is the next relation is equal to beta is equal to e minus pi minus 1 upon 2 root 2 1 upon 2 upon root 2, and then gamma is equal to you have a pi plus 1 upon 2 uh, 1 upon 2 root 2, sorry, this is 2 upon root 2. So this is we calculate the coordinate vector of a this. So you have a this is clearly, so this is the, if you write in the matrix form, so this can be written as a minus 1 upon 2 root 2 minus e minus pi minus 1 upon 2 root 2 and pi plus 1 upon 2 root 2, this is equal to so this means we can just say that these are the coordinate vectors of this. So now I think I have to stop this class at this point, and then you can try these other finding the coordinate vectors of this. So thank you very much. We cover after this class all the portion of the basis and dimensions portion. In the next class we start the new chapter, and that is the chapter for linear transformation. And I just say that a little about the linear transformation. We know already know that the functions, so in place of a function we take a two sets, but in linear transformation we take a, in place of a two set we have to define take a two vector spaces and define a map, and that map satisfies certain properties, hold the condition some means homogeneity and additivity, then we can say that this is a clearly is a linear transform. Okay, now I stopped. Thank you. We have to continue in the next class about the linear transformation.